So today we'll be working on the simulation of heat exchangers. Actually, we have two exercises for the session. One is related to the simple heaters or coolers, and the other one is related to the real heat exchanger. So we'll work with the shortcut mode as well as the detail sizing mode of the heat exchanger as well. So let's skim through some basics before we jump into the real simulation. So here are a couple of terminologies and some governing equations you need to be aware of before getting into the simulation. Uh, we normally use two equations for the calculation of heat duty. One is related to the simple energy balance by MCP delta T, and the other one is relatively bigger framework that relates the design of heat exchanger, or at least when the area or the heat transfer coefficient is available, then we can determine the heat duty. Or if there is a heat duty available with us, then assuming some appropriate heat transfer coefficient value, we can determine the area of the heat exchanger. Then the heat transfer area coefficient is itself, it's a inverse of the heat transfer resistance, and principally includes 5 different level of resistances. You can imagine one convective resistance in the shell side, one convective in the tube side. Then there are two film resistances, one on the shell side and the other one on the tube side, and the fifth one is resistance due to the Fourier transfer of heat through the solid material. So these are the 5 resistances, and they account for the overall heat transfer coefficient. Then there is a log mean temperature difference. That is the common concept we use because of the non-linear temperature distributions across the heat exchanger length. They have different interpretations with respect to the parallel flow and the counter flow. But even the log mean temperature difference is not sufficient to accommodate the temperature distributions within multi-pass shell and tube heat exchangers. So for that case, we have to accommodate a correction factor for the log mean temperature difference as well. And that correction factor can be calculated by some empirical relations, including the temperature ratio and the effectiveness parameter. Normally you can find this correction factor in several textbooks as well, in the graphical form for different passes in the shell and the tube. So then there are concepts of temperature range and temperature approach. Temperature range is the difference for the same stream between inlet and the outlet temperature, but the temperature range temperature approach is relatively the more practical and often provides the limitations for the heat transfer, and that is the difference between outlet temperature of the hot fluid and the inlet temperature of the cold fluid. For heat exchanger simulations, we often come up with the error message, that is the temperature crossover. So whenever you find this term temperature crossover, immediately you should recognize that has to do something related to the temperature approach. So that is the thermodynamic limitation on the heat transfer. We cannot cross the temperature approach. For practical purposes, this temperature approach can be reasonably in the range of 5 to 10 degrees Celsius. So that is the minimum driving force for the heat transfer. And it also depends on the type of the fluids. If we have relatively cleaner fluids, then that can be stretched to the lower limit. And if there are dirty fluids that can cause fouling in the heat transfer surfaces, then this temperature approach limit is slightly above 10 degrees Celsius as well. We'll also notice this temperature approach in the Aspen simulation as well. So this is a very quick background. Then what Aspen Plus is capable of doing the simulation for heat transfer. In fact, there are 3 models that can simulate different heat transfer problems. First model is the heater. Heater is a very simple block. It requires only one inlet stream and the one outlet stream. So if that is the case, that means we are working only for the half of the heat exchanger. Uh, Given that this simple model, it is the most of the time it is the first option to choose when we have to determine the heat duty for a given heat transfer problem. Or if the duty is given, then at least we can determine what should be the outlet temperature of the process or the utility stream. Then there is a model with the name HeatX. That is the really powerful tool in the in the Aspen Plus. It can perform shortcut simulations uh, as well as the rigorous simulation where we can size heat exchanger and then use it the original geometry for the rating purposes or for the simulation purposes. So mind these three terminologies in with respect to HeatX block. One is the design, the other one is the rating, and the third one is the simulation. We'll come across these terminologies again inside the session as well. But whenever the subject is about the design of heat exchanger, that means we are principally talking about the calculation of area, or in detail in a rigorous model we are trying to calculate the geometry or the geometrical details of the heat exchanger with the given assumption that we use an appropriate heat transfer coefficient. So that is the design case. In the rating case, it is assumed that we do have the information of the geometry and we are trying to figure out whether that geometry is capable of doing a real time heat exchange service or not. With that option, we can determine the performance of the available geometry, or we can determine whether the geometry is oversized or undersized for given service. So these kind of problem solving capabilities lies with the rating mode. And the third one is the simulation. Simulation, again, it assumes some minimum geometrical information, or at least the information of heat transfer coefficient and the area. And assuming that we do have the heat transfer coefficient and the geometry, or at least the area of the heat exchanger, then we can assume all the geometry will be utilized for the heat transfer service. And then we can determine what should be, let's say, the outlet temperatures for that given geometry and the heat transfer coefficient. So these are the three modes that are entirely included with the HeatX blocks. Since HeatX block can perform rigorous simulations, and those simulations can also provide some mechanical information of the geometry. Also, we can estimate the fouling uh, with the same integration with the exchanger design and rating. That is another interface. Also, that interface is clipped inside the Aspen Plus interface as well. We'll use that interface today. So with that, we can determine the actual layout of the heat exchanger as well. How the tube bundle should look like, how the shell will look like with the let's say available TEMA class. uh, some of the limitations are there. For example, we cannot have exact information about the how many nuts or bullets or the flanges will be required, but should be the actual layout for the installation purposes. These are the mechanical details. These are beyond the scope of this session as well as EDR. Some other expert interfaces are available that has those kind of capabilities where we can rigorously design uh, the the installation layouts of the heat exchanger as well. And even we can determine the bill of material. There are several tema classes available inside the EDR browser. We can use those classes, and following the standard codes of the tema ASME, we can figure out the geometrical details of the heat exchanger. In fact, Aspen has developed two models for the heat exchanger simulations. One is the shell and tube model. It's mostly used for the uh, shell and tube type geometries. The other one is the air cooled model, and air cooled model is typically used for air cooled heat exchangers or the recuperators, and also that model is used for fired heaters and gas cooled heat exchangers. So these are entirely two different models, and Aspen has integrated both in Aspen Plus as well as in exchanger design and rating interfaces. Then there is another model that is for the multi heat exchange simulations when we have more than two streams. Normally in the heat exchanger, one is the hot stream, the other one is the cold stream. But in typical applications in refinery, one is the most common one is the LNG liquefaction. In those sort of applications, even we can introduce three streams, and this model is capable of simulating three streams inside a single large block, or you can call the heat exchanger. We won't be using this multi heat exchange model for this session. Then there is another block for the simple heat transfer calculations. We won't be getting into this block as well. So the first exercise is related to the simple heaters and coolers. Uh, I think we can skim through the heat exchanger theoretical section as well. Then we can do the simulations once. For the HeatX block, we can perform shortcut as well as rigorous simulations. Maybe you are aware of these two temperature profiles, one for the counter flow and the other one is for the co-flow or for the parallel flow. What we can define inside HeatX block, uh, the model modalities are shortcut and detailed or rigorous. The heat exchanger types can be shell and tube or cutlery boiler or thermosiphon, air cooled plate. There is a lot of variety that we can simulate inside HeatX block. Calculation modes, again the first three one, the design, rating and the simulation, these are the common ones, but still there is another calculation mode where we can determine the maximum fouling for the given heat exchanger service. Flow direction can be co-current, counter current and multi-pass. We can deal with the single phase, two phase, three phase, where the common one is one gas phase and the two liquid phases, that is the three phase. The geometry of the heat exchanger can be simulated horizontally or vertically. Um then I hope you can recognize this chart. Yeah, this one. So these are different Taman classes. Taman classifications of the shell and tube heat exchanger, where the first column is all the front head configurations, the middle column is about the shell different configurations, and the right one is about the rear head of the shell and tube heat exchanger. These are different configurations. Which one to select for a given service? It's not a simple task. It requires experience as well as uh, uh, detailed information of the process itself. The most common one I can figure out, the first two A and B front heads. The A is where we can entirely remove the front head from the remaining shell and the tube sheet, and the B is that is fixed with the bonnet, so that is not removable. So you can identify if we can remove the front head, that means at least we can approach the inside of the shell and we can do cleaning services. But of course, if we have more flexibility with the geometry, that will end up with the more cost as well. The second one is when the bonnet is integrated with the shell cover. That means we cannot directly approach inside the shell from this side. That will reduce the cost of the heat exchanger, but it will make the difficult cleaning or the maintenance. And there are a couple of other options. They are used as per the requirement of the given heat exchanger sizing. The common shells are single pass, two pass, or split flow. Single pass is in the counter flow. We have the two streams in the shell and the tube flowing in the opposite side. But in the two pass, we always have the duplication of each other. We'll have a mixed counterflow and the cross flow. At least when the tube pass is 1 and the shell pass are 2, we have the mixed flow of the counter and the co-current. In the split flow, the inlet nozzle is always in the center, and outlet nozzle is also in the center of the cell. But inside the shell, the flow splits between left and the right regions, or the front end and the rear end of the heat exchanger. And also there are replicas with the double splits and the divided flows. This J class, the divided flow, this is very much common when we have the heat exchanger for the condensation service. So the saturated vapors are the low quality vapors introduced from the from the top of the heat exchanger, and the condensate flows from the bottom of the heat exchanger. And you can identify the K type. This is pretty common as a reboiler of the heat of the towers or the distillation columns. These are the common ones: J type and K type, and also the E type is also the common one when we have relatively low duty, and the heat exchanger geometry is the simpler one. For the rear head, it totally depends what kind of service are we expecting from the heat exchanger. So then in that case, the fixed tube sheet, the L type, and the floating head, that is the S type, these are the common configurations. But of course, the other configurations are still available. Uh, Selection of the complete configuration, again, it depends what type of fluids we are trying to deal with, what are the temperature limits to deal the heat exchanger, how many are the what is the intensity of the thermal expansions inside the heat exchanger, and what should be the pressure drop, because all the stresses has to be accommodated for the heat exchanger geometry as well. And what is the duty of the heat exchanger? For the smaller duties, a single shell pass should be sufficient, but for the larger duties, maybe we need to have multiple shell passes or even the multiple tube passes as well. Then there are some selection guidelines from the TEMA classifications. I leave it up to you. You can have a look. These are the guidelines for the selection. What should be the front end, the shell, and the bonnet for different type of services. These are typically the thumb rules used in the sizing of heat exchangers. What should be the fluid allocation? Commonly, we perceive if we have the higher, how should we say, if we have the dirty fluid, relatively that can easily foul the heat exchange surface, then we preferably pass through the tubes because that cleaning is relatively simpler and easier. We can do mechanical cleaning or the chemical cleaning depending on the nature of the fouling. And if there is a relatively cleaner fluid, then we put it in the shell side. For cooling waters, there is a general recommendation we put it in the tube side for cooling purposes, but again, it depends what is the other fluid. This is not the only one. Sometimes it entirely depends what is the flow regime, because in the shell side we can create multiple turbulence areas to increase the heat transfer rates, but in the tube side we have only very limited scope to create the turbulence. So for the low Reynolds numbers, uh, we prefer to put that fluid in the shell side, but again, that is not the only criteria. We have to look up all the available criterias before deciding which fluid should go in which direction. Then there are some recommendations while dealing with the sizing of the heat exchanger. One of them is the velocity of the fluid. Sometimes we prefer to deal with the kinetic head rather than the velocity, or sometimes we simply take the velocity of the fluid. If the velocity is too low, that means we are trying to get into the laminar region where the heat transfer rates should be very low. But if the velocity is too high, that means we are in the region where we can end up with the vibrations for the heat exchanger, or even if the velocity is too high, that means we are putting the material in trouble, that can cause erosions as well. So the recommended velocity is, if we are talking about the cooling water, then this is roughly in the range of 1 to 2 meter per second. That is the very nominal velocity to deal with. Of course, it also depends on the material, which material can bear uh, uh, what meter per second of the fluid velocity as well. The typical cooling water outlet temperature shall not exceed 50 degrees Celsius. This is again a very common recommendation, because as we increase the cooling water temperature, that means we are allowing the dissolved solids to uh, undissolve and stick to the surfaces and cause the foulings. So typically we do not exceed 50 degrees Celsius. What is the common size of the shell? Again, these are the common recommendations. We move between 200 millimeter to 1.5 meter. These are the common shell sizes. Of course, we can increase the shell size, but again, that will be beyond the available standards. And then the manufacturer or the designer firm has to be very careful while exceeding or ignoring the available standard codes. And the shell size is typically not all possible numbers. It is commonly 200 or 250 millimeter or 300 or 350. We can have these common shell sizes. Then the tube diameters. The most common tube diameter is 1 inch outside diameter of the tube. But again, another common application is 19.05 millimeter outside tube diameter. These are the common tube sizes used for heat exchanger sizings. For different materials, you can also see what should be the thickness of the tube for a certain applications. Similarly, the tube length, common recommendation is we use 2.5 meter tube length for the minimum length. Of course, we can get below 2.5 meter and even higher than 6 meter, but again, those are not the common heat exchanger sizes. Again, in that case, we have to be very much careful. If we are getting out of the available standards or practices, then that heat exchanger should meet the required services and should be inside the safety margins. For the tube length, again, it is possible to get a tube length of 2.7 meter, but that's not the common practice. We have 2.5 or 3 or 3.5 meter length of the tubes. So that's the very background check. If you want to add anything in the general discussion, otherwise we can get into the simulations. All right. So the first exercise is, in a fertilizer plant, 45 tons per hour of saturated process condensate. That means we are talking about the saturated liquid. It's a condensate at 1.5 bar needs to be cooled down to 65 degrees Celsius. So that is the requirement. And we are asked to determine the heat duty required for the cooling process and develop a temperature profile as a function of heat transfer. So that's the first question. And the second is, if the cooling water is available at 4.5 bar and 30 degrees Celsius, then calculate the required flow rate of cooling water, given that its maximum allowable temperature rise is limited to 10 degrees Celsius. So that's the second part of the same question. So let's jump into the Aspen Plus interface and solve this exercise. So let's jump into Aspen Plus. Again, we'll start with the new simulation without any default template. We have only one component as water condensate. Duty? Duty is the heat transfer rate. Yeah, it's a heat transfer rate. It's a common terminology for the heat exchanger. So we can have in terms of kilowatts or joules per second, whatever the units you use for the heat transfer flow rate. Okay, so we have water as a single component. Can you recommend any property method? We can use steam NBS or IAPWS 95. Let's use this IAPWS 95. So that's it. We can run the properties environment. So since we'll be working with this simulation file, so don't forget to save this file. We can get in trouble at any point. So switch to the simulation environment. In the simulation environment, first thing is to draw the flow diagram. So we need to have the heater from the exchanger model palette, the first one in the exchanger. You can look for different shapes of the same model. It can be something like furnace, or even they put an icon of pump. It doesn't mean it's entirely a pump. It's again the heat transfer calculation model. It can be a valve or a fan, air cooler. So let's use the simpler one, the heater. Give it a name, anything you want. Then we need to have one inlet stream and the one outlet stream. Pick a material stream, and also you can read at the input port. It's a feed on the left. You can attach multiple feed streams, or it can be minimum one feed stream. Let's call it uh, process in PN. And the outlet product can be only one stream. We cannot have multiple product streams from the heater block. So let's call it P out. So that's it. You can escape from the selection tool with the escape button, and then to simplify the flow sheet, you can control A, control B, and control J. Control A, control B, and control J. These three commands will streamline all the streams and the blocks. Then we need to give the inputs for the material stream, and then inputs for the block. First, jump into the input port inlet line, that is P in. You can proceed directly, double click on the inlet line, or you can browse from the navigation pane. The temperature is, we don't know, but we know is it's a saturated condensate. So temperature is not well known so far. One option is we can work in the properties environment and figure out if it's a water and it's a saturated liquid at 1.5 bar, then what should be the temperature. Other option is the same interface gives an option to pick from temperature, pressure, and vapor fractions. So one input is pressure 1.5 bar, and we can pick the other option for instead of temperature. So we can take vapor fraction. So the pressure is 1.5 bar and the vapor fraction should be 0 or 1? 0. So this is the common term that we use for the bubble points and the dew points. So the bubble is equivalent to the boiling point and the dew is equivalent to the condensation point. So 0 for the boiling point and 1 for the condensation point. For the pure component, it's the same thing. But for the multi-component system, they can have entirely different meanings. So the flow rate is 45 tons per hour. So let's choose the mass flow rate, 45 tons per hour. And for the composition, let's pick any fraction, mass or mole or volume, whatever you use. It's a pure component, and we need to pick 1. So that's a pure component. We are done with the input specification of the inlet stream, then we have to move to the block. Let's see what we can define in the block. So navigate to the heater input page. For the input specifications, we need to have two input specifications. One is the temperature. We do know we have to cool down the condensate to 65 degrees Celsius. So let's place the temperature to 65 degrees Celsius, and we have to give one more specifications. Uh, as of now, we don't have that one. The minimum assumption is we can assume that there is no pressure drop in this case. So for the zero pressure drop, if there is no pressure drop, we can place a value of 0. Aspen assumes that the 0 means no pressure drop. Otherwise, we can put up the same value of 1.5 over here. That will be the same meaning, 1.5 bar. So both have the same meaning. If you do know the pressure drop other than 0, then you can put a minus value over here. So minus will be considered as negative from the inlet pressure. So that's it. With this, we can run the simulation. So where can we view the results? Under the block, in the results tab, and the results are to achieve 65 degrees Celsius temperature of the condensate. We have the duty. You can check duty in kilowatts. So that's 2210 kilowatt. So that's a heat duty. That's the answer to the first question. At the same time, you can check the steam results, summary of the steam, at least the temperature. So the outlet temperature we have specified. For the inlet temperature, we have just specified the vapor fraction, and that vapor fraction corresponds to a temperature of 111.34 degrees Celsius. That's a boiling point corresponding to 1.5 bar. As of now, there is nothing special to read on the stream summary, but we can further consider from this block is the duty curve. We can plot the temperature versus heat duty inside the two temperature limits. So for that purpose, we have to go to the second option under the block, H curve, and we can create a new H curve. And the page is very straightforward. We have the independent variable of duty or temperature. So you can place any of the two. Let's change the temperature. We have a better specifications of the temperature. One is 111.3 and the other one is the 65, and let's interpolate between the two temperature limits. You can select any number of data points. Nothing else is required for the specification, and you can run the simulation with this. To view the results, you can go to the third tab on the same page. Here are the available results, temperature, and the heat duty. So temperature and the heat duty. Let's plot this. Before plotting, let's shift the units to kilowatt because we can better recognize these numbers. And once this is okay, we can go to this plot option with the custom plot, where we have liberty to plot as per our requirement. What x-axis should we choose? Totally depends whether we are interested with the heat duty or with the temperature. Okay, so you can plot anyway. So this is how the temperature versus enthalpy flow or the duty looks like. Uh, with the inlet temperature, we don't have any duty value, it's a 0. But at the specifications of 65 degrees Celsius, the heat duty is around 2210 kilowatt. So this is how you can reach the temperature duty curve. And anywhere in between, if that's a task, let's say we have to achieve 80 degrees Celsius, then what should be the duty? Either you can simulate there, or you can just read from this plot. So that's a very simple exercise. The next task is uh, we have to determine the flow rate of cooling water. The temperature, pressure, and the exit temperature of the cooling water specifications are known. Uh, what we can do for that simulation, already we have, this is not heater, this is cooler. Let's make a correction, because we are cooling down the process stream. It's a cooler. Of course, it doesn't make a difference, but we should be clear with the tags. So cooling water should be used for this service. What we can do, we can pass the same duty information to another heater block that will take cooling water as the inlet and heated cooling water as the outlet. So for that purpose, let's use another heater block. Let's call it heater this time, and there should be one inlet stream as cooling water in. Let's say it's a CWN, and one leaving stream, let's call CW out for the cooling water out. And we can pass the heat duty from the cooler block to the heater block. So for that purpose, you need to take heat stream. It's in the expanded view of the streams. So you can pick this heat stream, this option at the top, and we have all the ports where we can connect this stream. Let's take the cursor over here. It says the heat stream connection port. Let's take the same duty from here and pass it to the heater block and connect there, and let's call it a Q. Everyone got this? So we need to connect the two blocks with the heat stream. So take the heat stream, take input from the cooler block and pass it to the heater block. So that means we have already provided one equation to the heater block. Earlier we had provided two informations, two specifications. Now one has been provided by the heat transfer. We have to provide only one of those. So let's specify the cooling water inlet stream. The inlet temperature is 30 degrees Celsius. Pressure is 4.5 bar. Flow rate we don't know as of now, uh, but we do know it's a pure water. For a moment we can randomly give any flow rate. We don't know what it should be, but we'll come back to exactly determine the flow rate. Let's give any number. What should be? We don't know. Let's say the other one was 45 tons. Let's take this 50 tons per hour. It's a very random number. We have to justify it and we have to determine the corrected one. Because the requirement is the discharge temperature of this cooling water should not be more than 40 degrees Celsius. We have to meet that limitation. So that's it with the inlet stream. Move to the heater block and specify it. And you see there is only 1 degree of freedom over here. What can we give over here? The minimum assumption can be there is no pressure drop. So let's put a 0 value over there. And with this we can run the simulation. So let's run the simulation. What should we notice? The first thing, what is the temperature rise of the cooling water? Because we have made an assumption and we have to rectify it. So for that purpose, you can go to the stream results of the heater block and see the temperature 71 degrees Celsius. So, but the message is we have to reduce the temperature to the given constraint of 10 degrees Celsius rise, and for that purpose, we can increase the cooling water flow rate. How we can do that? One option is let's randomly try in different flow rates. The other option is we can work with the inherently available option of the design specifications. The design specification option is under the flow sheeting options in the navigation pane. We can also work with the sensitivity analysis, that is under model analysis tools, and also figure out for 40 degrees Celsius discharge temperature of the cooling water what should be the flow rate. So we can use either of the two options to figure out the flow rate. The convenient one is the design specification, so that you can use this option for any kind of such constraints where you have to determine a certain value for a given constraint. You can use the design specification option. Let's create a new design specification. Create the new one. Here we have to satisfy three tabs. One is the define, and define is what is the objective function over here. So that is the define part. The other one is the specs part. Specs part is the numerical values of the objective function, and the third one is the manipulated variable. So let's first specify the manipulated variable. How do we specify this? This is a very common approach in flow sheeting options as well as in the model analysis options. Aspen Plus gives a very sequential procedure to pick all the variables. First is the type of manipulated variables. For stream variables, we need to figure out from the option of stream variable. These are different groups. And if we are working with any variable that is associated to the block, then we have to pick the option from the block variable. The block variable is the common one that we use. It's the fourth option in the list. And similarly for the stream variables, you can go near the end of this list where it's a stream variable. So be careful in the selection of the variable. It should be from the list of stream variable. It's very near at the bottom. And then we need to specify which stream are we talking about. We are talking about the manipulation of the cooling water inlet stream. So that should be CW in. And the variable is, it's a mass flow rate. And then we also need to give a lower limit and the upper limit where we can vary the stream variable. Let's use lower limit is the 45 tons and use any upper limit. What should we use? Let's say 100. We don't know what it should be. We can just guess and change the units to tons per hour. Tons per hour. Be careful. This number 50 and 100, they are associated to this unit. So various specified, and then let's define the objective function. Objective function is the cooling water outlet stream temperature should be 40 degrees Celsius, not beyond that. So for that purpose, create a new variable. Let's create a new one. Give any name. Let's say TCW out. It's a temperature of cooling water outlet stream. Then for convenience from the category, let's pick a stream because this again variable is associated to stream. And in the right options under reference, what is the type? It's a stream variable. Go to stream variable, that is at the near bottom. uh, Stream that we are talking about is the CW out. We are trying to fix the temperature of CW out, and the variable is temperature in this case in degrees Celsius. So we have defined the variable for the objective function, and let's move to the specs block. Here the spec, the first information is exactly the variable that we are talking about. You can type the variable. The other option is you can right click exactly on the cell, right click on the cell, go to the variable list, and you can see all the variables that we have defined anywhere in the simulation file. All the variables will appear over here, and you can simply click and drag it to the spec block. You can drag it over here. So following this activity or this exercise, at least we are sure we are using the same variable that we mean. And the target is the target temperature. It should be 40 degrees Celsius, and we can define a reasonable tolerance. What should we use? Let's say 0.01. So any value 40.01 or 39.99 is acceptable for us. You can tighten the tolerance or you can loosen the tolerance. So that's it. We can run the simulation again. I'm seeing a warning. Anybody else? Good. Okay. So let's see what is the warning. One option is we can check the status. It's a button at the very bottom next to the status. It's the same page, and we can click on the solver to see what is the warning message. So the warning is either solution outside bounds. So that's a clear indication. The bound we have defined 50 and 100 tons per hour. So the solution lies somewhere beyond that limit. Let's first cross check. Again, go to the design specification where we had defined the objective function, and we can move to the results of that tab. Here you can see what are the results. So we started with the 71.9 degrees Celsius where the flow rate was 45,000 kilograms per hour, and it used maximum flow rate 100 tons per hour, that is close to 95,700 kilograms per hour, and we ended up only with the 50 degrees Celsius. So that means we are clearly lying outside the upper limit. We have to increase the upper limit. So go to the inputs of the same design specification then, and increase the limit, that is under vary. Increase the limit to, let's say, 200 degrees Celsius, 200 tons per hour. Increase the upper limit and run the simulation again. Again there is a warning. Let's cross check if we are even close to the results. So we are pretty close to the results. Not enough. With 200 tons per hour, we are still at 40.49 because the tolerance is 0.01. This is still not acceptable. That means we have to have even more flow rate. So again, go to the vary and under the design specification and even increase this one. Any number you prefer. I just randomly put a number of 250, and now the results are available without any warning. So let's see what should be the cooling water flow rate. To achieve a 40 degrees Celsius outlet temperature of the cooling water, we have to have 190,423 kilograms per hour. So that's the answer to the second question. So to meet the duty given in for the condensation, we have to have this much cooling water flow rate. Everyone managed to solve this? No? Okay. uh, that's it for the first exercise. Then we'll be doing second exercise, but before that let's take a 5-minute break. Try to stick to 5 minutes break because we have very extensive exercise. Okay, so let's move to the next exercise. We have to be very careful for this exercise. Okay, so before jumping into the next exercise, let's do one change in the previous one. uh, Go to the design specs tab and deactivate it, otherwise it will always create a mess for us. Yeah? Just you have to uncheck this active button, so that means this design specs won't work anymore. For the second exercise, let's first build the flow sheet. To build the flow sheet, we need to take any of the model from the second group, HeatX. So just a very quick tip while taking this HeatX model, because we can put hot fluid in the shell or we can put it in the tube. So of course we can work inside the specification of the block as well, but the good practice is always be sure even before taking this block. For example, if you expand this one, there are a lot of configurations available. These are simply the icons and slight difference in the input ports. Otherwise, the background maths is always the same for all the models. So the first icon is simp ht, the second one gen ht, simp hs, and the gen hs. Can you just identify what it could be? Simple or the generic, but what should be the second letter, hs and ht? Can you just identify whether the hot fluid is in the shell side or in the tube side? So it's about that. So in this case, how should we proceed? Whether we should put condensate in the tube side or the cooling water in the tube side. So another common practice is if the fluid is hot, everything else is acceptable, then the put hot fluid in the tube side. So if we put the hot fluid in the shell side, at least there is a room for the heat loss from the shell to the environment. So for that reason, we can put the hot fluid in in the tubes. But on the contrary, it's also recommendation that put cooling water in the tube side. So we have the two recommendations in front of us. So then choice lies up to us as of now for the preliminary exercise. So what should we choose? Let's say the hot fluid in the tube side, condensate in the tube side, and cooling water in the shell side. So for that purpose, take the second icon. Uh, Name anything. Let's say HeatX, and connect 4 streams. Take a material stream. Be careful, we have to have the 2 material streams inside, inlet and 2 outlet. Take a material stream, and if you take the cursor to the any input port, let's say this is the tube side, and it also requires the hot fluid. So that means when we are working with this simulation, we have to put the hot fluid in the tubes because we have selected that particular icon from the available models. So let's say P in 2, use this or as you prefer. Similarly, the process outlet stream, P out 2, and in the shell side it's a cold fluid. It also gives an indication of cold required. This is cooling water in 2 and cooling water out 2. So with these 4 streams, the input, the flow sheet is complete. Let's save the simulation. Escape from the selection tool. We need to define all the inputs of cooling water and the process stream, inlet streams. Again, the specifications are the same as we were working previously. The process stream inlet temperature we don't know, but we do know the vapor fraction of the inlet, that is 0. The pressure is 1.5 bar. Mass flow rate is 45 tons per hour. Be careful in the composition section. Always select a fraction if you are working with the composition. Of course, we can define the fractions composition in terms of the flow rates as well. Then go to the cooling water inlet specifications. The inlet temperature is 30 degrees Celsius, pressure is 4.5 bar. Now we do know what should be the mass flow rate. We can get it from the previous activity. Mass flow rate is 190,423 kg per hour. You can copy the same number. One 423 in kilograms per hour, and the fraction is 1. So then we have to move to the HeatX block and define the specifications of the HeatX block. So here we can define exactly the information that the outlet temperature of the cooling water should be 40 degrees Celsius. So that is the only required information over here. As a general tour of this interface, we have a specification tab. On the top left corner, we can work with the shortcut as a model fidelity, or the detailed or the rigorous ones as a shell and tube, kettle, thermosiphon, air, or plate. So the below options are the rigorous calculations where we can size or rate, but the first option is very shortcut option. Then here we can also specify whether the hot fluid should be in the tube side or the shell side. If you have rightly choose the icon, then we don't need to specify anything over here. And you can also select the flow directions in the counter or in the co-current or in the multipass. Then in the calculation modes, you can notice design mode, rating mode, and the simulation mode. The most frequently used 3 modes. And then we have another mode, that is the maximum falling. For the maximum falling, we have to have the exact geometrical information as well. So the problem is, we do know what should be the outlet temperature, but we don't know what should be the area requirements or the overall heat transfer coefficient. We don't have any information like that. So at least we can provide the information that we do have. So if you pick the option from the drop down of the exchanger specification, that it should be cooling stream outlet temperature or the cold stream outlet temperature, and the cold stream outlet temperature is 40 degrees Celsius. And here is the minimum temperature approach. So that is the thermodynamic limitation. Whatever happens, we cannot violate this. The minimum driving force or the approach temperature should be 1 degree Celsius. This is just a constraint, not any input specification. If Aspen Plus finds there is a violation, it will generate error message against this. We can put a higher approach temperature. That means Aspen Plus will follow the same violation next time. So with this, we don't have to do anything else. We can run the simulation. So just run the simulation. So what should we notice over here? What do you expect? We should have, for the design phase, we haven't provided any geometrical information. Aspen Plus should be capable to calculate at least the area using exchanger design equation Q equals UA delta T. But for that purpose, we have to have some heat transfer coefficient. So what is the heat transfer coefficient in this case? If you go to the same tab, same window in the U method, on the U method tab, it has assumed some value, and these are the default values based on the phase specific. These are just the default values. If we do have the better information of the overall heat transfer coefficient, then we can specify the value in the first option. Constant heat transfer coefficient, we can specify that value over here. Again, this is a default value. If we have heat transfer coefficient from any math equation with the power law, or we don't have the geometry as of now, film coefficients, any option available to determine the heat transfer coefficient, we can use that. But as of now, we are totally blank. We don't know what happens. So that's why we have randomly taken a default value. Again, for the log mean temperature difference, we have just taken a constant value, and that constant value is from the default math equations that we can take the temperature differences between the hot streams and the cold streams and take the logarithmic mean. So from that information, it has taken a constant value. Otherwise, we can specify with the geometry, or we can provide an appropriate math correlation to calculate that. For the pressure drop, we haven't specified any pressure drop. By default, it's a 0. You can notice under pressure drop. If you do know any pressure drop value, you can specify over here for the hot side as well as for the cold side. So these are additional informations. We have to be careful about it when we are simulating the base cases. The next is to view the results. Go to this thermal results option. It's under the same block in the thermal results tab. So all the temperatures and pressures are listed in the summary. The inlet and outlet temperature of the process stream and of the cooling water utility stream. Those 4 options are perfectly fine. We can look more results from the exchanger details in the third tab. The calculated duty, you can shift the units to see what is the duty. It's a 2210 kilowatt, and for that purpose, using the assumed heat transfer coefficient value that we have just looked at, it calculated this 50.95 square meter. That is the area requirement, assuming that coefficient value to meet this duty. So it has taken the same actual heat transfer heat exchanger area, the same value. You can notice this is the information heat transfer coefficient we have just assumed previously. It has multiplied with the area to determine the UA value, heat transfer coefficient multiplied with the heat exchanger area, and it has calculated the corrected log mean temperature difference. So now we have better information of the area. Let's see, we can just randomly assume another area value, 40 square meter or 60 square meter. That means for the different area, we can run the rating or we can run the simulation, because we do have some more information compared to the previous case. So let's go to the input specification page, setup page. and shift the mode from design to the rating. So shifting to the rating mode, it requires additional information, and it's pretty understandable. If we are working with the rating, that means we have to have some geometrical information, or the minimum is we have to have some information about the area of the exchanger. Let's put any random value, uh, 60 square meter, and we do know we have provided exchanger area more than desired to meet the duty. And you can run with this, just run the simulation with this 60 square meter in the rating mode, and go to the thermal results and see the exchanger details once again. You see, now the required is 50.95, and we have provided 60 square meter, and that is 17.76% over designed. So the additional results are still the same. LMT, UA, these are still the same, but with the rating, it has calculated the performance in terms of under designed or the over designed to meet the given duty. So this is how the rating mode works. Let's same way go to the third option, the simulation mode. With the simulation mode, it has bypassed one of the requirement, and that is what should be the cold stream outlet temperature. That means for the simulation, it will take the new exchanger area to determine what should be the discharge temperature of the cooling water. So that is the simulation. This is how the simulation mode works. You can run the simulation and again go to the thermal results, and now you can notice the difference. The discharge temperature of the process stream, it has changed to 60.40. Previously it was 65 degrees Celsius. So that makes a perfect sense because we are providing a bigger exchanger area than the minimum required as of the previous case. So for the bigger area, it should reduce further the process stream temperature. So the objective of viewing these three options was to figure out how these three options work. In the design, we are trying to determine the area requirements. In the rating, we are trying to use the area to figure out whether the exchanger performance is as per our requirement or not. And with the simulation environment, we are exactly using the area that we have provided to figure out what should be the discharge stream specifications. So this is how three calculation modes work. What should we do now? Let's explore the rigorous simulation or sizing of the exchanger. How do we design or size the exchangers? For that purpose, put it back to the design mode. Let's delete the other two heaters because they can conflict or provide unnecessary confusions. We don't need the previous two heaters. Select them and delete them. If you see this error message, that is because of the design specifications. So go to the design specifications and delete it, because that design specification, it called some stream informations and we have deleted those streams. So just delete the design specifications. So the interface is relatively clean now, and even to cleaner it further, reinitialize to flush all the results and run it again. Just to manage, we are with the default simulations that we were at the very beginning. So these are just the makeups. Just reinitialize is this option, this reset option. Sorry, I'm just using a different term. What it does, it flushes all the previously available results and make the simulation from calculations from the default values. So once you are at this, the simulation is clean, results are available. That means now we are ready to size or design the geometry of the exchanger. So everybody on this page, we have to run in a very thick exercise now. So there is a separate interface in Aspen Plus, in Aspen products, that is named as exchanger design and rating, and we can do all the design exercises in that interface, exchanger design and rating. And also Aspen Plus has embedded that interface within Aspen Plus, and that is, if you can notice, EDR in the same folder, EDR options, EDR browser, even below some are EDR shell and tube, and this EDR is exchanger design and rating. So what we can do, if we want to jump from the Aspen Plus interface into the EDR interface, we can directly enter, double click the exchanger in the previous page. Either we can jump from here, from the shortcut to this detailed option, we need to pick a different radio button. This is one of the option. We can proceed from this way. Or the other option is we can separately open EDR interface and call this simulation in the EDR as a baseline. So these are two different options. So the first option is shifting from the shortcut option to this shell and tube model fidelity, and the other option is directly opening the EDR interface. Personally, I prefer to work in the EDR interface because that gives a more liberty to play with. So let's open exchanger design and rating. It should be installed, Aspen exchanger design and rating. And we can call this simulation in the EDR browser. So this is the first look of EDR browser. If you have any pre-solved exercises, they can appear over here. Otherwise, enter new, and from the new option, it gives shell and tube thermal design option and shell and tube mechanical design option. Let's stick to the preliminary exercise of shell and tube exchanger and create. Pick the first option. And this is the front interface. We can entirely work in this interface even by defining the process conditions, or we can call the process conditions from the previous simulation if you have saved that file. So let's call the Aspen Plus file inside the EDR interface. For that purpose, go to the file, import option, file import option, and import from the Aspen Plus, from Aspen Plus, and just locate where you have saved the previous file. Just browse that file inside the EDR interface. At front, it will display all the exchanger blocks in the Aspen Plus file. Since we have only one, whatever the name you have defined, it will recall that name, and you can simply click the import option. It will give a second pop-up where it provides some basic information what we are going to import. In fact, we are going to import the process informations. The inlet temperature, outlet is not shown over here. CW in. Let's import the information. So if you have noticed, previously there were some cross at couple of tabs, now they have gone. What we need to notice over here is first have a look on the process tab. On the second tab in the console. Again, this is the similar interface. On the left, we do have the navigation pane, and then we have multiple tabs. In the process, These are the process flow conditions. These are in pounds per hour. That means we can switch the units for better understanding. Switch to SI units. So the mass flow rate of the hot side inlet and the cold side inlets are given. These are exactly the same information that we have called from there. Pressures are there. Inlet temperatures are there. Rest is it can calculate, and exchanger duty is there. It can calculate the discharge temperatures from the duty. This is the same duty 2210. Additional information for the sizing purposes is we have to provide allowable pressure drop and the fouling resistance. We have to provide this information. So let's take the same information from there, from the example, and put it there. And tube side allowable pressure drop is 0.6 bar. Before that, let's have a check, because it also gives option of location of hot fluid. If you can notice in the geometry tab, it also gives another indication where the hot fluid is. Hot fluid is in the tube side. So just to cross check. And then the fouling resistance, shell side is 0.00017. Okay, there is another information we just skipped for this specific exercise. Given in the problem statement, consider cooling water in the tube side and condensate in the shell side. So that means we have to make the adjustment. So the condensate is the hot fluid, and it should be in the shell side for this specific example. So go to the geometry option and pick the location of hot fluid in the shell side, just to be on the same page. So now we need to make the adjustment. The hot side pressure drop is in the shell side, and that is 0.1 bar. So that's why I was confused. And the other one is 0.6, because these fouling resistance, they are very much specific to the fluid. So if we shift the fluids, that means we are playing with a different degree of freedom. So we need to be specific for this. And the shell side or the hot side resistance is 0.00017, and the other one is 0.0003 in meter square Kelvin per watt. These are very critical numbers. Be sure you are giving the right information. So that's it. This is the minimum information we have to provide. Aspen Plus has taken all other default informations for the preliminary sizings. Let's cross check what it has given. It has taken some default TEMA classification. You can notice the front has taken as the bonnet bolted. If you want to have the removable cover, that is the TEMA A, or other one. Similarly, the shell, by default it has taken one pass shell. If you are working with a different example and you need a different shell, then you can pick other option. Similarly, for the rear head, by default it's taken as the bonneted. Otherwise, you can take the integral or the U-tube or the floating rear head. So these are entirely based on some experience or available standard informations. The default tube size, it has taken 19.05 millimeter. That is very common, less than 1 inch. And the tube pitch is taken. Similarly, if you are working with the different tube patterns, then you can take other than 30 triangular tube pitch. Baffles, yes, there should be baffles inside the shell. Type is single segmental. You can take double or triple or any other option of the baffles. Orientation, most of the time it's horizontal, but if there is any requirement for the vertical, because that will affect the flow regimes as well. The default material is taken for the tubes, carbon steel. So these are the default informations. There is a lot of information that we can play with, but let's stick to the default information. uh, you can also scroll down to a couple of other options. In the input tabs, you can define the company name, because these can be printed on the TAMA specification sheets. Location, or the service unit, or the job, or multiple other options. Even for that specification sheet, there can be a revision number or the job numbers. They will be printed on the specification or the data sheets. Some options related to the applications, you can scroll down. If there is anything of interest, you can play with. Again, that is another outlook of the process informations. Then under properties, it has calculated some default informations for the properties, including conductivity, viscosity, and enthalpy values for the cold stream as well as for the hot streams. You can rigorously play the input specifications of the geometry over here. For the shell heads, for the tubes, it gives a lots of other options. Even the details of the baffles. We don't have any other information. We can just at least scroll down what kind of options it gives. For the construction materials, we have the multiple options for the shells, for the tubes, even tube sheets, even for the baffles, what kind of materials we are selecting. You can choose any of these. And some design codes, these are pretty important in this case. By default, we are working with the two standards. One is the TAMA standard, the other one is the ASME standard. So all the shell and tube geometrical informations or related information is taken from the TAMA specifications or TAMA standards, and all the informations related to the pressures, they are taken from the ASME code section 8 in the division 1 or 2. So these two standard codes are pretty important when we are sizing the shell and tube heat exchangers. If you are working with the different standards, it has to be taken very carefully. Material information is taken from the ASME standards. So that's it. We don't have to define anything from our side unless we are pretty much sure what we are going to define. And with this, we can run the simulation. Just click this run option. And see the message at the bottom. Run shell and tube, that is completed. And always the first pop-up window is the warnings and the advisories. There shouldn't be any serious warning in this case. If there is any serious warning, so it takes all the required information very carefully. But if we are playing from ourselves, if we have defined some non-standard conditions, that means we can expect some errors or serious warnings over here. You can notice additional advisories if they are relevant to your case, but advisories are just for the informations or for the improvement purposes. And warnings, they should be taken carefully. We can omit the warnings, not the errors, but still it's good to look in the warnings as well. So this is a very common warning. To look into the Aspen properties, that is taken from the BJAC. This is again a method from where Aspen Plus takes the properties of the fluids. So we have the exchanger sizing. The default sizing is available with us. We only need to view the results. How to view the results? First is how Aspen Plus calculated all these options, and that is given in the optimization path. So Aspen Plus made at least 5 different attempts. And what are those attempts? It has taken different shell sizes. You can notice 307 millimeter till 438 millimeters. It has taken different shell sizes. It has taken different tube lengths, uh, required area to actual area ratios. With this, it has calculated pressure drops, calculated some baffles, spacings, number of baffles, because with the length of the tube, number of baffles will change. Uh, it calculated number of shells and number of tube passes. We have already defined one shell pass from the Tama class, but it calculated the tube passes and it's still the same one. Even it calculated the total price for that given design, and run multiple operational checks. The most important operational checks are whether the velocity of the fluid is so much so we can expect any erosion or vibrations inside the shell or inside the tube. It checks for the vibrations, and for the given heat exchanger size, we are not expecting any vibration. That's a good sign. If there is any option of vibration over here, that means whether you are defining the geometry yourself or Aspen is taking by default, that is not acceptable at all, because that uh, exchanger will not be operationally feasible. The second is kinetic head check rho v square. By default, we should be in the safe limit of the velocity. So that is checked by the rho v square. And the third is whether any section of the tube is unsupported by the baffles or by the tube sheet. All these options should be no, strictly no. If there is any option of yes over here, that means that exchanger is not acceptable. So by default, Aspen EDR has made these 5 entirely different calculations, and then it displayed a most feasible option at the end. And the most feasible option is at number 2, that means this second size. Can you just predict why it has taken this most feasible option at number 2? So one option is minimum cost. It's not the minimum one. The minimum one is $18,000, and this is next to the minimum $19,000. But the design status, EDR was unsure about the feasibility of the design itself. So whether the design is the most appropriate one for the given exercise or not. So it was doubtful. It put a status of a near feasible, but the other one, second, third, and the last options was perfectly fine with respect to the quick checks and with respect to the hidden feasibility checks. And it has taken the first option, that it is pretty sure that this is the most feasible option. So that is not the most economical one, but the most feasible one next to the economical one. So this is how Aspen Plus makes different calculations and displays one of those results. Then we can recap some results. Uh, Shell ID, it has taken shell inside diameter of 336 millimeter. If this shell ID is according to the industrial practices or the feasible standards, then you can stay with the same. Otherwise, you can go back to the input specifications and change this shell ID, because it has taken some random values. And now it's up to us to make sure that input specifications or the results over here, they are as per the practical standards, or they should be acceptable to the manufacturer. We cannot take any random value. You can cross check what are the most common shell IDs. Uh, for example, in this option, the shell diameter, the shell inside diameter for actual plants, it's not 336 millimeter. It's either 300 or 350. That means it has made some calculation, but that calculation may not be the common practice in the industry. So that means we need to change the shell ID. Similarly, you can consider the tube lengths. It has taken 4.876 meter, but this is a common practice. You can check the common practices. The tube length common is 4.5 meter or 5 meter or 6 meter. It doesn't mean we cannot fabricate the exchanger with these details, it means this is not a common practice. The manufacturer can manufacture with the results of these specifications, or better use the standard practices. Similarly, the pressure drop it has calculated on the shell side, that is zero point 0.06. We have defined a minimum allowable pressure drop in the shell side, that was 0.1 bar, and this is even less than that, that is acceptable. Or the pressure drop in the tube side is zero point 0.2 bar. This is again below the allowable pressure drop, that is a good thing. It has calculated the baffle spacings, number of baffles. You can consider total number of tubes are 134. Coefficients on the shell side and on the tube side, film coefficients, the duty is still the same that was given as a default input information. The most interesting thing is the TAMA standard sheet. If you have defined the overall informations of the company, locations, then item number, specifications in the earlier page, then they should have been displayed over here. Otherwise, this is a common TAMA specification. Anybody working with the shell and tube heat exchanger or the manufacturer, they can easily read this specifications. It gives information of the fluid, flow rates, the temperature inside and outside, some physical properties including density, viscosity, specific heat, latent heat, pressures. Inlet pressure is 1.5 on the shell side. By subtracting the pressure drop on the shell side, it has defined the discharge pressure as 1.43, and similarly for the tube side. Fouling resistances, we have provided the default values as the allowable foulings. Some construction details, even the sketch of the exchanger geometry is also given. The corrosion allowance is given. This is again another very critical information. What should be the corrosion allowance for any shell and tube heat exchanger to be fabricated and employed for a given service? Channels, bonnets, floating head, no information given. It has given information about the Rovi square in the nozzle, that is 390, that is the kinetic head. In the bundle entrance level and the bundle exit level. Weight of the shell, weight of the complete exchanger, including if it's completed, if it's filled with water. These weight informations are given. Separately, bundle weight is also given, and some overall information. So this is again a different display of the same information. Then you can move to the other performance results. A lots of information is available over here. I just want to point out film coefficients. They are pretty important for at least for chemical engineers. Mean temperature difference informations are given. Vibrations, no vibration, that is well required. You can click and even look at the details about the vibration calculations. Some information about the heat transfer related to the coefficients, even the Prandtl number, Reynolds numbers in the shell and tubes, they are also calculated. And from this, you can quickly have a look what should be the flow regime inside the tubes and inside the shell. Even for the mean temperature differences, you can have a second look. Some information related to the pressure drops, flow analysis. There's a lots of other information. It entirely depends what kind of problem we are solving and what is exactly required for our case. The velocity is very critical. In a normal practice, the velocity, if we are dealing with the cooling water, it should be in the range of 1 to 1.5 meter per second for a feasible. If it's less than that, less than 1 meter per second, then there is an option that the fouling will build up very quickly. If it's more than 1.5, that means we are pretty much in the zone where erosion can happen very quickly. Erosion of the tubes are the materials. uh, just let's have a quick look. Some mechanical summaries are given. The most important one is the setting plan. Setting plan under mechanical summary. So this is how the exchanger will visually look like. Front head, rear head, the shells, they are given in separate views. How the tube sheet will look like. 134 tubes will be aligned exactly like this. You can count this number of tubes. Even you can notice the tube pitch. This is entirely the triangular pitch. Information related to the cost and weights are given, and also some information about the calculation details. So these are all the results. This is really a very powerful tool, even so powerful. If you can size with the common practices, we can give exactly this standard specification sheet to any manufacturer, and he can get the heat exchanger manufactured, and we can just deploy for any related exercise. I leave other options up to you, because the shell ID is not the normal practice, tube length is not the normal practice. I have provided some information. I will encourage, just go back and try different uh, designs, and try to have a look what kind of heat exchangers you can come up. This is not the only thing. So we have defined a geometry. Now there is another exercise. If we work with this geometry, what should be the discharge temperature of the cooling water? We need 40 degrees Celsius. If we define the 40 degrees Celsius for the water, then what should be the discharge temperature of the process fluid? We have to cross verify the performance. So normal practice is you do the sizing, and then based on the size geometry you do the rating once again. That rating will exactly inform the designed exchanger sizes, whether they are very much appropriate for the given service, it's under designed or it's over designed. And if it's over designed or under designed, in any case, how much we can extend, or what maximum capacity we can pull up from the given exchanger. So that is the simulation mode. So that means now we can save this information, and we can call the same information back in the Aspen Plus interface and do the same rating and the simulation exercises, just to cross check whether the designed geometry is appropriate or not. As of now, this geometry is not up to the mark. We have to work on it, especially with the common practices. This is not up to the common practice. But due to the time limitation, let's save this exercise. Let's name HeatX 0123. Give any name. Go back in the Aspen Plus interface and switch from shortcut to shell and tube rigorous or detailed fidelity. And on this interface, we are not going to size exchanger anymore, but we are going to specify the geometry, and we can import that geometry from the EDR file. So I hope you got the flow. Let's browse this. So once path is given, you can convert it. So now directly it has changed from the design mode to the simulation mode. To my practice, if you do exercise like this, import the geometry and directly run the simulation in the simulation mode, then quite oftenly I experience the errors. So let's try if we still experience the errors, or we have to figure out the other way. So let's run it. So it's a very common today. So far, I couldn't figure out what is the error, but somehow I figured out the troubleshoot. So how to do that? When it's in the simulation mode, don't accept it. First run the design mode. Once design mode is successfully run, then we can shift to the rating mode and run the simulation once again. In the rating mode, we can view the results first to figure out what changes has been made so far. And now the outlet temperature is 64.9 degrees Celsius for the process stream, and for the cooling water it's 40 degrees Celsius, still the same. So let's have a look on the exchanger details. In the exchanger details, the heat duty is 1968. So that means the slightly duty calculation has changed. Previously, it was 2210 kilowatt, but now the duty is changed slightly, and accordingly, the required exchanger area is also changed. And the actual area based on the geometry designed by the EDR browser, it is higher than the required exchanger area. So you can notice the difference between required exchanger area and the actual area. The actual area is 6.64% over design. So that is in the safe limits. So still, to meet the same service, to drop from the saturated condensate to nearly 6500 degrees Celsius, the new calculation suggests that the required duty is different from the previously calculated duty, and even the area is slightly different. So that's a difference between having no geometrical information and having a detailed geometrical information. So during the design mode without any geometry, we can obtain a slightly different results, but once the geometry is available with us and we have rigorously designed the heat exchanger, so with the new available information, we can expect slightly different area requirements. Besides, let's go to the third option of the simulation. If we utilize all the over designed area, then what temperature of the process stream we can obtain? Let's run the simulation and view the results once again. So now the simulation with the new over designed geometry, not only the discharge temperature of the process stream is affected, but also the discharge temperature of the cooling water is affected. So the discharge temperature of the cooling water with over designed geometry slightly increased from the 40 degrees Celsius to 40.37 degrees Celsius. But at the same time, due to having higher surface area, the process stream temperature dropped from 65 degrees Celsius to 63.18 degrees Celsius. So that can be a potential case when a new heat exchanger is installed on site and all the available geometry is effectively utilized for the heat transfer case. And you can notice the difference between required exchanger area and the actual exchanger area that has been used for the simulation purpose. And even the corrected LMTD has slightly changed based on the new heat transfer problem. Still, if it is required even to increase the design margin from 6.6% to even higher, so if that is required, then we don't need to get back to the EDR browser. Rather, we can work inside the EDR from this option. So here we can play with all the geometries as we need. We can work with the shell ID. Also, we can work with the tube length. We can fix the tube length as per our own requirement. If it is required, we can shift number of baffles or the spacing between the baffles. We can entirely now work inside the EDR browser in Aspen Plus. Since it's a single pass exchanger, there is only one tube pass and one shell pass, and the flow is counter flow, so that you can notice the difference in the profiles as well. The cooling water temperature changes from 30 degrees Celsius to close to 40 degrees Celsius. It increases along the length of the exchanger. But on the other side, the temperature of the condensate changes from 111 degrees Celsius to close to 64 degrees Celsius. So this is how the counterflow profiles can be viewed. The current design, the current design, it fulfills the required service to lower the condensate temperature from its saturation conditions to 65 degrees Celsius. But since the geometrical details are not as per the common practices of the shell ID and the tube length, so I suggest to slightly work on this and make this exchanger a more feasible fabrication option where the geometrical information is close to the acceptable limits of the industrial practices. The last exercise of this assignment was to determine the cost of the exchanger. Although we have determined the cost of the exchanger in the EDR browser as well, but here in the Aspen Plus interface, we can take advantage of the activation dashboard of the cost analyzer to determine the cost, not only the cost of the heat exchanger, but also the cost of the operation as well. And for that purpose, either we can proceed to this activation dashboard or we can work with the second ribbon named as economics. To determine the cost, first we need to activate this. So once the economic dashboard is activated from this option, if you have better information of the stream prices and the utility prices, then you can proceed with these options. And even for the cost options, you can choose an appropriate template where all the cost index, sizing details of the different units, and also the tax information is stored. You can use an appropriate template. Let's run with the US IP template. So the first option has to be mapping of the exchanger with an equipment stored in the Aspen library. So proceed to this mapping, but before that it asks to run the simulation once again. We can just map with the default basis, size the equipments. We don't need to custom size any of the equipment. So here all the unit operations available in the flow sheet will be displayed. Since we have only one unit with the HeatX name, so it will be displayed. To map differently, by default it has mapped the exchanger with the Tama shell and tube exchanger. To map differently, let's enter from this icon, and here go to the available exchangers. The exchanger can be a heat exchanger or a reboiler or furnace. Let's go to the heat exchanger. Here we have a different options to choose from. Keep in mind, the Aspen Economic Analyzer does not rely on the geometry of the EDR browser. Rather, it internally runs the sizing based on the volumetric models and internally determines the size of the exchanger. And then based on the size and different cost index, it determines the cost. So we need to pick from these options what kind of heat exchanger are we expecting. Either the Tama shell and tube heat exchanger, or the air cooled, or the plate and frame, or double pipe. There is a long list of available model geometries in the Aspen library. Let's stick to the first option, Tama shell and tube heat exchanger, and that's it. We can click OK. Once this is done, it has already sized. Otherwise, we need to run the sizing by ourselves as well. And then we can evaluate the cost of the exchanger. It runs the Aspen Process Economic Analyzer in the background and displays the result from this dashboard. We can view the dashboard with the enlarged option, and here we can see the cost. This is the first outlook of the cost. The capital cost of this exchanger will be 1.3 million US dollar, and the utility cost per year will be 35,544. Let's click to view the details. Notice where the results are stored. In the navigation pane, in the last option of the result summary under the equipment, you can see these options. The quick summary is the total capital cost for this exchanger is 1.370 million US dollars. Operational cost is also given. The utility cost is directly displayed on the dashboard as well. The desired rate of return is 20% to recover the cost of the exchanger. Only the specific equipment cost is also listed as 22,000 US dollars, and the total install cost is also given. For the utilities, since we have not defined any specific utility in this case, but this utility is related to the cooling water, and the flow rate is given, and the cost per hour is also given. For the unit operation, you can see the details. These are the similar numbers as of the summary, but in a more expanded view. Information related to equipment and information related to the TAMA heat exchanger as well. For any case, if we want to have a different equipment sizing, as of now, this class is BEM. The front end as B, shell as E, and rear head as M. If we want to have a different TAMA class, or we can match with the EDR browser TAMA class, then we can take advantage of a different options from here. The design temperature and pressure of the exchanger is also given. The operational conditions are also given. The tube length and number of tubes per shell is also given. You can notice the difference. Previously, we had calculated 134 tubes per shell, and here 98 tubes are given. If we want to have a different geometry, then we can rigorously play over here, and we can try to match the geometry with the geometry of the EDR browser. This is the geometry determined by the Aspen Process Economic Analyzer. And we have the liberty to change any of the number and make the adjustment. For the case of exercise, change the number of tubes from 98 to 100. Once we change this, and then we can evaluate the process economic cost once again. And then we can cross check what is the equipment cost this time with adding two more tubes of the same length. So that was all we were intended for this exercise. I invite you to perform some sensitivities for this exchanger where you can figure out a better exchanger sizing. Maybe you can play with the multi-tube pass or play with the different tube lengths as per the industry standard practices. Figure out the cost of the exchanger, figure out the operational feasibility of the newly designed exchanger, and print the TAMA sheets. You can print the TAMA sheets from the EDR results. So for that purpose, go to the EDR browser. And from the EDR browser, go to the result summary and the TAMA sheet. Here in the TAMA sheets, it gives multiple options to print the results. Go to the print options. And here in the print options, you have all the options to select and print from the available Aspen interface. For example, in the result summary, if you are only interested in printing the TAMA sheet, then you can choose this option. If you are also interested in printing the overall summary, then you can print it. You can print a soft copy, or you can directly connect it to a hard printer to print. So let's save the print, call it a TAMA sheet, open this option. So here is the printout of the TAMA sheet that we have uh, just printed out. You can notice the surface area, all the details, and overall summary of the exchanger. So if you are interested, you can print a different option related to this exercise. So that's all for today. Hopefully this exercise was of pretty interest for you. Designing heat exchanger is a very tedious task. It's not a one go solution never. So you have to try a multiple geometries, cross-check with the industrial standards, cross-check if the designed heat exchanger is operationally feasible or not, and then make the decision.